Well, hi guys. We are starting our calculus unit, and the very first thing that you study in calculus is this concept of a limit. And I'm going to teach you what they mean and how to answer them. So first of all, let's get another phrase out of the way. Whenever we're talking about a limit, you are going to be declaring an intended height of a function. Even if that function doesn't get there, we want to know what the goal of the function is. So an analogy would be like this page, what is this race car driver? What is its goal? Even though it's not at the finish line, we know that the race car driver wants to get to the finish line. So let's see if we can hear him. Yeah, so you think he got there? Well, he's pretty close here, so we could probably say that the limit of this race car driver is that finish line. So that's his intended height or his intended position. Now, when we are answering limits, we're going to do these one of three different ways. First of all, we're going to do some plug and chug, or maybe make a table. We're going to do some algebra, and there's other things to do besides just algebra. I guess but I'm going to call it algebra for now, because factoring is going to be involved. And we can also just take a look at a graph. We can do it graphically. So we're going to do all of these. So let's get started. All right, let's get the notation out of the way. When we're answering limits, you're going to see this LIM, and that's short for limit. Underneath that, you're going to see X. This means we're looking on the X-axis, and X is approaching this number C. So this tells our eyes where to focus on the X-axis. This is where to look on the X-axis. So that tells us the number. And of course, f of x is just our function, and this right here is going to be the answer to our limit. So this is our answer. And this is going to come from a y-coordinate. We're going to be looking and seeing if the graph is heading towards y-coordinate. So let me tell you how to read this. This is read as the limit as x approaches c of f of x equals L. Let's say that again. The limit as x approaches c of f of x equals L. So let's take a look at a table. Here I have the limit as x approaches -1 of x plus 1 over x squared minus x minus 2. Now, one thing we can do is a plug and chug approach. Let me get to my select here. So if we were to go look at our table in our calculator, what we're looking at is this x is approaching -1. So we want to be focused around -1. So you see these x values here? All of these x values are very, very close to -1. These three are a little to the left of -1, and these three are a little to the right. So if we plug those in, what we're looking for is the y value heading towards a specific number. So you plug in -1.1, you get -0.322. Then if you plug in -1.01, we get -0.332. And then -1.001 gets us to -0.333. That's called from the left. I'm plugged in numbers approaching -1, but from the left. Then if we do the same thing from the right, if we plug in -0.9, we can see all of these values. So what does it look like this is approaching? Well, it looks like this is approaching -0.333 from both directions. Now, why didn't we just plug in -1 to the function and ask it where is it heading? Why don't we just plug -1 in for x? Well, if we do that, we're going to get -1 plus 1 is 0. And then on the bottom, -1 squared is +1. Minus -1 is +2, and then -2 is 0. And 0 divided by 0 is something called indeterminate. That means that in its current form, we are not able to figure out what that is. And 0 divided by 0 is not 0. It's called indeterminate. So this means you've got some work to do. Here we used a table. And here's another thing we could have done. We could have done some factoring. I could have factored the bottom into x minus 2 and x plus 1. And look what happens. I've got a common factor here that can cancel, and I can simplify this limit down to 1 over x minus 2. Then if we plug in -1 for x, we get -1/3, which is what we can see from the table. And that's the answer to our limit, is -1/3. See if we got it right. Oh, yay. Okay. All right. Other things you can't the table might not help you, especially if you don't know your sine values. So let's take a look at another approach here. We want to know the limit as x approaches 0 of sine of x over x. Now, if we were to plug in 0, we would get the sine of 0 over 0. And of course, the sine of 0 is 0. So this is, again, the indeterminate form. Now, in this example, I cannot factor this. So let's go see if we can't look at this graphically. And again, this is where our eyes are going to be looking. We want to look when x approaches 0, what is the y-coordinate? So let's go take a look at this graph. So here's a picture of sine of x over x. And we want to focus in around x equals 0, which is right here in the middle. We'll go purple. So here's where we're focusing, and let's look at the graph. From the right, the graph looks like it's approaching 1, and from the left, the graph is also approaching 1. So visually, we can see that the answer to our limit is 1 because that's the y-coordinate. As we focus in on 0, that's where the graph is heading. So this answer should be 0. And let's see if we get it right. I've got to do my eraser here. We did. I don't know if I just said the answer should be 0, but the answer is supposed to be 1 because we just saw that from the graph. Let's take a look at this other one here, this square root of x thingy. Now, if we plug in 0 for x, we're going to get the square root of 3 minus the square root of 3, which is 0 over 0. And again, we get indeterminate. And here there's no algebra to do, but there is something that we can do, and it's called multiply the top and bottom by the conjugate. We've done that several times this year. So I can multiply the top and bottom by x plus 3 plus square root of 3 divided by the square root of x plus 3 plus the square root of 3. So I've multiplied the top and bottom by the conjugate. So let's see what happens algebraically. I've got here like an a minus b times a plus b. So if I FOIL all this out, I'm going to get x plus 3 minus 3. And you can check that yourself if you do all of that foiling. That times that, that times that, that times that, and that times that. Now on the bottom, I'm just going to have x times the square root of x plus 3 plus the square root of 3. 3 minus 3, of course, is 0, and those x's cancel, and this can reduce down to 1 over the square root of x plus 3 plus the square root of 3. That's called multiplying by the conjugate. And what that allows me to do is now I can plug in 0 for x. So if we plug in 0 for our x, we get 1 over 2 square roots of 3. We actually get an answer, which is the answer to our limit. That's a pretty small number. 1 over 2 square roots of 3 is about 1 over 3.4. So I don't know, a little less than a third. Let's go take a look at the graph and see where it's headed. Again, we're looking as x approaches 0, so let's go look at this graph. So here is 0, and you can see it's a little bit above 0.25. So let's see what this answer actually works out to be. Got the decimal in here. And it's 0.2887, which if you do 1 over 2 square roots of 3, that's what you're going to get. Okay, not all the time limits exist. If you've ever seen Mean Girls, when the girl goes, the limit does not exist. That is an answer sometimes when a graph does not have an intended height from both directions. And what you have to look at is you have to look at the graph from the left and from the right, and if those are different values, then you're going to say the limit does not exist. If you have unbounded behavior, this means the graph is heading straight up or straight down, and like up to infinity or down to negative infinity, or if you have oscillating behavior. No, that's not working. Oh well. Alright, so let's take a look at this, the limit from the right and the limit from the left. So we've got these two friends that are trying to meet up and they're going to go somewhere. And this person from the right is going at a different y value than this person from the left. This is an instance where the limit does not exist. Let's look at this graphically. So here I've got a piecewise function, and piecewise functions are where you have more than one equation. It's got f of x equals, we open up brackets. So we've got f of x equals 1 if x is greater than 0. And x is greater than 0 means positive values of x. So you can see all of these positive values of x. We've got the line y equals 1. Now, for all of the values less than 0, I've got f of x equals -1. And so this is called a piecewise function. I've got two different equations for different intervals on the x-axis. And this is an instance where from the right, the graph is approaching +1. But from the left, the graph is approaching -1. So we would say that the limit does not exist because from the right and from the left, they're not approaching the same y value. So here we would say DNE for our answer to our limit. Let's just write this down. The limit as x approaches 0 of f of x equals does not exist. All right, so here's an example of unbounded behavior. This is a graph about 1 over x plus 2. It's been shifted to the right 2. And I'm sorry, this is 1 over x minus 2. And we can see here, if we zoom in on 2, this graph from the right-hand side is heading straight up, and then from the left-hand side, that's heading straight down. This is what we call unbounded behavior. This happens at vertical asymptotes. That's my sine of x graph. So here's another example of a limit that does not exist. As we approach 0 from the right, this graph is going straight up. You can notice here, even on the scale, all the way up to 9,000. This is going towards infinity. And from the left, it's heading the same direction, but it's going towards infinity. We wouldn't say that this stops at 7,000 or 8,000 or even 10,000. It's heading straight up. So this is an example of unbounded behavior, and we would say that this limit does not exist. All right, so let's take a look at oscillating behavior. This is sine of 1 over x. And this graph, when you zoom in at 0, is doing some crazy stuff in here. And let's see if this limit is approaching a specific value. You might select here. I probably already had it. But if we plug in 2 over pi, it's 1. 2 over 3 pi, it's -1. 2 over 5 pi, it's 1. 2 over 7 pi, it's -1. And as we are getting smaller and smaller and smaller, these values are getting closer and closer to 0. This thing's just bouncing back and forth between -1 and 1. And that means that that's an example of oscillating behavior, so we would say that the limit does not exist. Now let's take a look at some last specific graphic examples here. I've got a crazy picture here of a piecewise function. Let's answer a few questions. What's the limit as x approaches 7 of f of x? So this is where we're supposed to focus our eyes. We want to look close to 7. So here we go. Here's 7. Now from the right, this graph is approaching this y value of -1. And from the left, this graph is also approaching that y value of -1. And even though the graph is not filled in, the intended height, or the goal of the graph, was to reach the value -1. So that's the answer for that limit. Let's try another one. What about the limit as x approaches 3 of f of x? So I look here at 3, and from the right, the graph is approaching -1. But what's happening from the left? From the left, it's going to a different value. It's going to 2. Since these don't line up, we say that the limit does not exist because they're not heading towards the same y value. Okay, let's just do one last example here. What about the limit as x approaches -2 of f of x? Well, here we can see -2 from the right and from the left. It's approaching the same value, and it looks like it's a little bit smaller than 4. So I'd say it's close to 4. All right, so I will see you guys tomorrow, and we will practice this limit stuff.